unveiling the infinite, from Quinn's Atlas to the multiverse. What if the boundaries of our knowledge are merely the shifting outlines of an ever-expanding map? What if, rather than reaching an ultimate end, each discovery simply peels away one layer of mystery, only to reveal another? Throughout history, humanity has attempted to chart the unknown, whether by sketching the contours of the Earth or by unraveling the fabric of the cosmos. Just as explorers once set sail across uncharted seas, scientists now embark on intellectual voyages that stretch far beyond the visible universe into realms we can scarcely imagine. In 1828, amateur cartographer Edward Quinn completed his life's work, the Historical Atlas. Published posthumously, this ambitious project depicted human knowledge as a flickering light, gradually dispelling clouds of ignorance. With each passing epoch, the map revealed more of the world, mirroring the expansion of European exploration. His initial vision was narrow, rooted in the lands of the Euphrates and Tigris, but as the pages turned, the world grew ever larger. The Roman Empire emerged, the age of discovery unfolded, and by the early 19th century, the clouds had completely lifted. From Quinn's perspective, the entire world had been unveiled, no more lands left to explore. Of course, this was a Eurocentric view. In China, India, Australia, and the Americas, the same story would have been told from a different origin, with different blind spots, surrounded by their own darkness. But Quinn's metaphor of knowledge emerging from obscurity applies to more than just geography. Science, too, has always battled its own clouds of mystery. Every discipline, whether astronomy, biology, or physics, begins in uncertainty, its truths hidden beneath layers of the unknown. And just as the surface of the Earth was once cloaked in fog, so too has the universe itself been veiled, its deepest workings concealed from view. In the past few centuries, humanity has turned its gaze upward, shifting from mapping continents to mapping the heavens. With increasingly powerful telescopes, we have peered deeper into the cosmos, uncovering stars, galaxies, black holes, and exoplanets orbiting distant suns. We have looked back over 13 billion years, capturing the faint afterglow of the Big Bang itself. With remarkable precision, we can even predict the far future of the universe, the dimming of the last stars, the evaporation of black holes, the dissolution of matter itself. It would be tempting to conclude that we are approaching the limits of cosmic knowledge. But history warns us against such arrogance. In 1888, astronomer Simon Newcomb confidently declared that astronomy had reached its final frontiers. Just 2 decades later, Einstein's theory of relativity upended our understanding of space and time. Time and again, declarations of finality have proven premature. Science thrives on revolution, and the greatest discoveries often emerge where we least expect them. Today, physicists find themselves in much the same position. Standing atop towering equations and wielding instruments of unprecedented sophistication, they seek to penetrate deeper into the fog, not just of distance, but of fundamental reality. The mysteries they confront are no longer confined to the distant past or far-flung galaxies. They are woven into the very fabric of existence, hidden within the microscopic interactions that govern particles and forces. As our knowledge of theoretical physics has expanded, what once seemed speculative has gradually solidified into plausible and even probable reality. Among the most radical yet increasingly compelling ideas is the notion of the multiverse. This is not a single theory, but a collection of interconnected hypotheses, each proposing that our universe is merely one of many. Some models suggest a vast cosmic landscape of bubble universes, each with its own distinct laws of physics. Others propose an infinite number of parallel worlds, where every possible outcome of every event plays out across an endless spectrum of realities. Still others imply that entire universes might be born from quantum fluctuations, blinking in and out of existence beyond the limits of our perception. If these ideas prove correct, then the cosmos is far stranger than we ever imagined, a layered, fractal-like tapestry of existence, where each universe is but one ripple in an infinite sea. Just as Quinn's atlas gradually exposed the lands hidden beneath the clouds, modern physics seeks to lift the cosmic veil, revealing a universe that is not a singular entity, but a bewildering multiplicity of realities. Welcome to the multiverse, a place where every possibility exists, where boundaries dissolve into infinities, and where the pursuit of knowledge is, and always will be, an endless voyage into the unknown. Level 1. The Great Debate and the Boundless Cosmos. What if our universe is just one of many? What if the cosmic horizon that we perceive is merely a boundary of observation rather than a true edge of existence? These questions, though deeply philosophical, have become central to modern cosmology. Before we explore the vast implications of a multiverse, we must first retrace the steps that led us to our current understanding of the universe's scale. In April 1920, the Smithsonian Museum of Natural History in Washington, D.C., became the stage for one of the most significant debates in the history of astronomy. On one side stood Harlow Shapley, an astronomer renowned for mapping the Milky Way. Opposing him was Heber Curtis, an expert observer who had unwittingly discovered relativistic jets in the galaxy M87, though he did not yet understand their true nature. The central question of their debate: just how big is the universe? Shapley championed the idea of a compact cosmos, asserting that the entire universe was contained within the Milky Way. He acknowledged that astronomers had observed strange spiral nebulae, but argued that they were merely structures within our own galaxy. Curtis, however, painted a radically different picture. He argued that these spiral nebulae were not part of the Milky Way at all. Instead, they were entire galaxies unto themselves, vast island universes separated by immense distances. If Curtis was correct, the universe was far larger than anyone had previously imagined. Though the debate ended without a definitive resolution, the question was far from settled. Meanwhile, on the opposite coast of the United States, an astronomer named Edwin Hubble was about to change everything. Hubble had recently joined the Mount Wilson Observatory in California, where the newly constructed 100-inch Hooker telescope, the most powerful in the world at the time, had just been installed. His first target was the Andromeda Nebula, a hazy structure that had perplexed astronomers for centuries. Was it part of the Milky Way, or was it something more? Hubble's breakthrough came through the study of Cepheid variable stars, stellar beacons whose luminosity pulses in a predictable manner. Henrietta Swan Leavitt had discovered that the period of a Cepheid's pulsation was directly linked to its intrinsic brightness. By measuring this pulsation, astronomers could calculate a star's true luminosity and, in turn, determine its distance. When Hubble applied this method to the stars within Andromeda, the results were shocking. These stars lay far beyond the confines of the Milky Way. Andromeda was not a mere nebula, but a galaxy in its own right, containing billions of stars. In 1924, Hubble sent a letter to Shapley, stating plainly that the universe was far larger than he had believed. Shapley's response: "Here is the letter that destroyed my universe." With this revelation, the boundaries of the cosmos expanded dramatically. Soon after, Hubble went further, showing that galaxies were not static, but moving away from each other. The universe itself was expanding, a discovery that would lay the foundation for the Big Bang Theory. As technology improved throughout the 20th century, telescopes probed deeper into space. What had once been measured in thousands of light years soon became millions, then billions. Yet, even as our reach extended, a natural question emerged: is there a limit to how far we can see? In 1964, two radio astronomers, Arno Penzias and Robert Wilson, detected an unusual hiss of radiation emanating uniformly from all directions. This was the cosmic microwave background, CMB, the afterglow of the Big Bang itself, its photons traveling for 13.7 billion years. This relic of the early universe forms a natural boundary, a cosmic horizon beyond which no light has yet reached us. This, of course, invites an even more profound question: what lies beyond the observable universe? Building on Einstein's relativity and Friedmann's equations, theoretical physicists realized that the observable universe must be just a fraction of a much grander whole. Given the finite speed of light, we can only see the regions of space from which light has had time to reach us. But logic dictates that beyond our cosmic horizon, there must be more stars, more galaxies, more planets. The universe, it seemed, was not just vast, it might be infinite. If the universe has no spatial curvature, as observational evidence suggests, then it extends infinitely in all directions. If it is infinite today, then it always has been. Even at its birth, when it was inconceivably dense, it would still have stretched without bounds, merely growing less dense over time. What we perceive as our observable universe is but a tiny bubble within this infinite expanse. This concept forms the foundation of what physicist Max Tegmark calls the level 1 multiverse. In this model, the cosmos is infinite, and beyond our horizon lies an unending ocean of galaxies, each forming its own observable bubble of space. Infinity carries profound implications. If space extends forever, then within it, every possible arrangement of matter must eventually occur. Given an infinite amount of space, some regions of the universe will be nearly identical to our own. Others will be slightly different. And at unimaginable distances, there will exist precise duplicates of our own Milky Way, our own Earth, even our own selves. Statistical probability suggests that a cosmic doppelganger of you exists somewhere. Tegmark estimates that such an identical copy would be located approximately 10 to the power of 118 meters away. Though they are causally disconnected from us, these parallel versions of our world must exist within the infinite expanse of the level 1 multiverse. Yet this is just the beginning. The level 1 multiverse is the most conservative extrapolation of physics, a mere extension of space as we understand it. But as we climb further up the ladder of multiversal theories, reality becomes even more bizarre. Level 2, the fine-tuned universe and the eternal multiverse. Why does our universe possess the precise set of physical laws that govern its structure? Could they have been different? These may seem like abstract, even philosophical questions. Yet, as our understanding of physics has deepened throughout the 20th and 21st centuries, they have become impossible to ignore. In the 1960s, physicist Robert Dicke proposed that the forces of gravity and electromagnetism appeared to be delicately balanced. If they deviated even slightly, stars would fail to shine, and life would be impossible. As physicists probed deeper into the nature of fundamental forces, further examples of this fine-tuning emerged. Fred Hoyle discovered that minuscule changes in nuclear forces would result in a universe devoid of carbon, the very element necessary for complex chemistry. Later, Steven Weinberg observed that even a slight increase in dark energy would cause the cosmos to expand too rapidly for galaxies and stars to form. The more scientists examined the cosmos, the more they found that its fundamental properties appeared finely tuned for complexity. If the universe had been even marginally different, we would not exist. This led to an unsettling realization. Our universe is not just any universe. It seems uniquely structured to allow for life. But why should that be the case? The answer, paradoxically, may lie in the very nature of the multiverse itself. To explore this concept, we must first understand inflation, a period of rapid cosmic expansion proposed by Alan Guth. According to Guth's model, inflation occurred in a trillionth of a trillionth of a trillionth of a second, smoothing out the universe and seeding the formation of galaxies. It provided an elegant solution to many cosmological puzzles, making it a cornerstone of modern physics. However, an immediate paradox arose. How could inflation have ended uniformly across the entire universe in such an infinitesimally brief moment? Early calculations suggested that inflation would not conclude everywhere at once. Instead, in some regions, it would persist indefinitely. This posed a significant problem. If inflation did not end uniformly, how could our universe have formed in a coherent, structured manner? Rather than abandoning the idea, physicists refined it. By the 1980s, a new generation of theorists, Andre Linde, Andreas Albrecht, and Paul Steinhardt, developed a more robust version of inflation, one that embraced its apparent chaos. Central to this refined model was the concept of the inflaton field, a fundamental field that drove inflation forward. This revised framework introduced a radical notion. Inflation does not end everywhere simultaneously. Instead, it gives rise to an infinite number of separate, self-contained universes. While one region ceases inflating and forms a structured cosmos, inflation continues elsewhere, generating new universes in an ongoing. In this picture, our Level 1 multiverse, an infinite extension of space containing galaxies much like our own, is merely a subset of a far grander structure, the Level 2 multiverse. Within this model, our observable universe is just one bubble among countless others, all separated by ever-expanding space and time. The fabric of the cosmos itself continuously gives birth to new universes, each crystallizing into existence as inflation recedes locally. Yet, within this endless spawning of universes lies a critical consequence. Each universe can possess different fundamental properties. The conditions that define physics, the strengths of forces, the masses of fundamental particles, even the number of spatial dimensions, could vary dramatically from one universe to another. Physicists have speculated about the nature of these alternative universes, and their conclusions are stark. The overwhelming majority would be dead, sterile, and devoid of complexity. If the fundamental constants were even slightly altered, many universes would never form stars, planets, or the conditions necessary for life. However, within this vast landscape of barren worlds, there exist rare pockets of habitable universes, just like ours. This statistical perspective suggests that we should not be surprised by the apparent fine-tuning of our own cosmos. Rather than being the result of design, it is simply a consequence of the vastness of possibility. We find ourselves in one of the exceedingly rare universes that permit complexity because that is the only kind of universe where conscious observers can exist. This is the essence of the anthropic principle. We observe a life-permitting universe because only in such a universe could observers arise to ask the question. In this view, our finely tuned universe is not unique. It is just one successful roll of an infinite set of cosmic dice. While eternal inflation provides one pathway to a Level 2 multiverse, it is not the only theoretical framework that suggests multiple universes. Another idea has its roots in an ancient concept, the cyclical nature of existence. In Hindu cosmology, the universe is described as eternal, undergoing endless cycles of creation, destruction, and rebirth. Interestingly, a similar idea has appeared in modern physics. Throughout the 20th century, cosmologists, including Einstein, entertained the notion that our universe might not be a one-time event, but part of an ongoing cycle. Within the equations of general relativity, certain solutions allow for a universe that repeatedly expands and contracts, a cosmic cycle with no absolute beginning or end. This vision of a cyclic universe was appealing. Rather than being born from an inexplicable singularity, the universe could be one iteration in an eternal sequence. Entropy, the measure of disorder in a system, is an unavoidable feature of thermodynamics. Every process in the universe increases entropy, gradually moving from order to disorder. Over immense timescales, energy degrades, and the cosmos inches toward thermodynamic equilibrium, a state of maximum entropy where no further work can be done. This poses a dilemma for a cyclical universe. If a new universe inherits the entropy of its predecessor, then with each cycle, disorder accumulates. Over infinite cycles, entropy would only increase, raising the question, how could a new universe emerge with the low entropy necessary for structure and life? If cycles have been occurring forever, why hasn't all order already been lost? This challenge led many physicists to abandon the idea of an eternally cycling cosmos in favor of a singular Big Bang. Yet, just as inflationary theory was refined in the face of early challenges, new variations of the cyclic model have emerged. Some propose that entropy resets under extreme conditions. Others suggest hidden dimensions that recycle energy in ways we do not yet fully understand. Whether through eternal inflation or an endless sequence of rebirths, modern cosmology increasingly points toward a reality far grander than the universe we observe. We exist within a cosmos that may be but one bubble in an infinite frothing sea, or one moment in an endless cosmic cycle. The deeper we look, the more the multiverse seems not just plausible, but inevitable. If there are indeed higher levels of reality beyond our own, then the story of the universe is still being written, playing out across landscapes we can scarcely begin to comprehend. And yet, we have only scratched the surface. The Level 2 multiverse is but one possibility, one rung on the ladder of deeper realities. As we continue climbing, the cosmos grows even stranger, more intricate, and more profoundly interconnected than we ever imagined. Recent Nobel laureate Roger Penrose introduced an intriguing cosmological framework known as conformal cyclic cosmology. According to his hypothesis, in the distant future of our universe, all matter will inevitably decay into radiation, leaving behind an empty, featureless cosmos. As the universe expands indefinitely, it will reach a state of such vastness and simplicity that its geometry becomes indistinguishable from the highly uniform conditions theorized at the Big Bang. This leads to a profound implication. The past and future are intrinsically connected, forming a perpetual cycle of cosmic death and rebirth. Penrose's perspective is not the only one to suggest a continuous generational process in the cosmos. In the 1980s, physicist Lee Smolin proposed a radically different mechanism for cosmic evolution, the idea that black holes might serve as the birthplaces of entirely new universes. Rather than emerging within the confines of our existing space-time, these offspring universes would manifest as wholly independent realms, each with its own set of physical laws. If true, then each stellar collapse leading to a black hole could signify the genesis of another cosmos, suggesting a reality where new universes are constantly emerging. Smolin extended his theory by incorporating a principle akin to Darwinian natural selection. He postulated that if the fundamental parameters governing each new universe could vary slightly, akin to genetic mutations, then only those that support star formation and black hole generation would persist. Universes that failed to produce such structures would fade into insignificance, effectively being evolutionary dead ends. Over countless generations, this natural selection process would favor universes with physical laws that optimize black hole formation, potentially leading to a multiverse teeming with star-filled, habitable realms. Although speculative, Smolin's hypothesis suggests that our own universe might be the result of such a selection process, finely tuned by an invisible evolutionary mechanism favoring complexity and structure. Another cyclic universe model has recently gained traction, echoing an ancient mythological metaphor, the phoenix. Just as the immortal bird perishes in flames only to rise anew from its ashes, physicists Paul Steinhardt and Neil Turok have proposed the ekpyrotic universe model, a fresh take on cyclic cosmology inspired by string theory. In their vision, our universe exists as a three-dimensional brain floating in a higher dimensional space. Periodically, these brains collide, releasing immense energy that births a new universe with low entropy, effectively resetting the cosmic cycle. Unlike previous cyclic models, the ekpyrotic scenario avoids the entropy problems that once undermined similar theories, suggesting that cosmic rebirth could be a natural and eternal process. Despite its elegance, the theory has yet to gain widespread acceptance, with many physicists remaining skeptical of the concept of higher dimensional brains. In the broader quest for a unified understanding of the cosmos, few names stand out as prominently as Edward Witten. Unlike many of his contemporaries, Witten's path to theoretical physics was unconventional. Initially drawn to history, linguistics, and even journalism, he ultimately found his calling in mathematics and fundamental physics, where his insights into the topology of space and time set him apart as a visionary thinker. In 1990, his pioneering work earned him the Fields Medal, an honor typically reserved for pure mathematicians. But Witten had his sights set on a grander ambition, the elusive theory of everything, a framework that could reconcile all fundamental forces into a single, coherent mathematical structure. The search for such a theory has been a long and arduous endeavor. While quantum mechanics successfully describes 3 of the 4 fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, gravity remains an outlier, governed by Einstein's general theory of relativity. The discrepancy between quantum mechanics and relativity has perplexed physicists for decades, suggesting that an even deeper, more fundamental theory must exist. Early attempts to unify these forces, such as the Kaluza-Klein theory, sought to introduce additional spatial dimensions, but ultimately fell short. Even Einstein, alongside brilliant minds like Hermann Weyl and Arthur Eddington, devoted years to this pursuit without success. By the 1970s, an exciting new framework known as supergravity emerged, founded upon the mathematical principles of supersymmetry. This theory posited that every known particle had a yet undiscovered superpartner, electrons with selectrons, quarks with squarks. However, supergravity encountered significant theoretical hurdles, and as physicists delved deeper, inconsistencies began to surface. Despite initial promise, the theory eventually faded from favor. Yet great ideas in physics rarely vanish entirely. In 1984, Michael Green and John Schwartz rekindled hope with the advent of superstring theory. The fundamental premise was as radical as it was elegant. Rather than treating elementary particles as indivisible points, superstring theory envisioned them as tiny vibrating strings. The different vibrational modes of these strings corresponded to different particles, unifying them under a single framework. However, the mathematics of string theory required additional spatial dimensions beyond our observable 3. Early formulations suggested as many as 26 dimensions, though refinements eventually converged on a more feasible 11, echoing the earlier supergravity theories. To reconcile these extra dimensions with observable reality, physicists proposed a mechanism known as compactification, wherein the additional dimensions are curled up into minuscule, intricate structures called Calabi-Yau manifolds. Though invisible to us, these hidden dimensions were postulated to influence the properties of particles and forces in our universe. Once again, hope soared that a true theory of everything had been discovered. But once again, the reality was more complicated. Instead of a single, unique theory of everything, physicists found themselves facing not one but 5 competing versions of string theory. The dream of a singular unifying framework seemed to be slipping away, replaced by a bewildering landscape of mathematical possibilities. Then, in 1995, at the annual String Theory Conference at the University of California, Ed Witten introduced a transformative idea. What unfolded in the wake of his insights would redefine the field and reignite the hope of unification. Witten's vision offered a new perspective on the fragmented theories, weaving them into a cohesive framework known as M-theory. This bold proposition suggested that the various string theories were merely different aspects of a more fundamental, 11-dimensional reality. M-theory posited that beyond the vibrating strings lay extended objects known as branes, capable of existing across multiple dimensions. The implications were profound. If correct, M-theory could provide the long-sought unification of all fundamental forces, seamlessly integrating gravity with quantum mechanics. Though the full mathematical structure of M-theory remains elusive, its conceptual breakthroughs have reshaped modern physics, inspiring new research into the deep fabric of the cosmos. The journey toward a theory of everything is far from over. Whether through conformal cycles, black hole progeny, brane collisions, or vibrating strings, physicists continue to push the boundaries of human understanding, striving to decode the ultimate nature of reality itself. As history has shown, even the boldest theories may fall short, but each step brings us closer to the fundamental truth that lies at the heart of the cosmos. Perhaps the 5 differing versions of string theory were not as distinct as they initially appeared. Perhaps, rather than separate competing theories, they were merely different perspectives of a single, unified framework. From this revelation, M-theory was conceived, igniting what is now known as the second superstring revolution. The meaning of the M in M-theory remains elusive. Some suggest it stands for mystery, others magic, but to many, it signifies membrane, reflecting how the one-dimensional strings of string theory extend into two-dimensional sheets, or branes, within the higher dimensional space. This conceptual leap helps to resolve some of the mathematical challenges of string theory, though it does not eliminate them entirely. In reality, M-theory is not yet a fully developed theory, but rather a framework, a guiding vision toward which physicists strive. It has, however, brought one crucial realization into focus. Originally, physicists hoped that the elusive theory of everything would be singular and unique, an elegant mathematical structure dictating the exact parameters of our universe, such as the mass of the electron or the strength of gravity. However, that hope was irrevocably altered with the advent of N-theory. N-theory suggests that the earliest moments of the universe were marked by extreme temperatures and simplicity. As the universe expanded and cooled, the fundamental physical laws did not emerge as a predetermined inevitability, but rather crystallized out in a process akin to symmetry breaking. Crucially, this crystallization was not unique. There exist countless possible ways in which the fundamental parameters of physics could have solidified. This idea introduced what is now known as the string theory landscape. The sheer number of possible configurations remains an open question, but estimates suggest an astronomical figure, perhaps as many as 10 to the power of 500 possible universes, each governed by a distinct set of physical laws. Some physicists argue that this multitude of possibilities is not merely theoretical, but reflects an actual, physical multiverse. In this picture, the multidimensional realm of N-theory, referred to as the bulk, contains an uncountable number of universes, each residing on its own membrane, or brane. Each of these universes, through its unique crystallization of physical laws, occupies a different region within the vast string theory landscape. The implications of this are profound. Just as the theory of eternal inflation suggests an ever-growing multitude of bubble universes, N-theory posits a vast, possibly infinite collection of brane universes, each differing in its fundamental physics. However, this vastness brings a sobering realization. The overwhelming majority of possible universes within the landscape would be sterile and lifeless, with physical laws so hostile to complexity that no structure, let alone life, could ever emerge. If M-theory's multiverse exists, then much like eternal inflation's cosmic lottery, the overwhelming expanse of reality would resemble a cosmic graveyard, where habitable universes are rare exceptions rather than the rule. And yet, improbability is not impossibility. Among the many lifeless universes, a few would possess just the right conditions to harbor stars, planets, and even life. In such a reality, our own existence is not a consequence of fine-tuning, but of statistical inevitability. We exist simply because we reside in one of the exceedingly rare universes where conditions allow for observers to emerge. Of course, M-theory remains speculative. The string theory landscape is a hypothesis, and the idea that universes exist as branes in the bulk is far from proven. But for many physicists, the internal coherence of M-theory and its deep mathematical structure make it an appealing and promising direction for future research. Whether it ultimately proves to be correct or not, the pursuit of M-theory continues to inspire new approaches to understanding the fundamental nature of reality. As our understanding of the cosmos expands, the possibility of multiple, coexisting level 2 multiverses emerges, some envisioned as infinite inflating bubbles, others as cyclic phoenix-like rebirths, and yet others as branes adrift in the higher dimensional bulk. The once impenetrable fog of ignorance is receding, revealing a complex and layered multiversal structure. But is this the final revelation? Is this the furthest extent of cosmic strangeness? Level 3. What if I told you that you are immortal, that you will live forever? What if I could guarantee that no matter what obstacles you face, you would ultimately emerge victorious? What if I asserted, with absolute certainty, that you would conquer illness and even death? That even with a gun pointed at your head, survival could still be ensured? Such claims might seem absurd, the ramblings of a madman. But we have now arrived at the level 3 multiverse, where immortality is not just a possibility, it is inevitable. To understand how, we must begin with a deceptively simple question that has reshaped our understanding of reality. What is the fundamental nature of light? By the 1800s, scientists had debated for over a century whether light was a wave or a particle. The decisive experiment that seemed to resolve this question was conducted in 1801 by Thomas Young, a polymath often referred to as the last man to know everything. His contributions spanned multiple disciplines, from medicine to linguistics. Indeed, he played a crucial role in deciphering the Rosetta Stone. But for our purposes, his most significant work lies in the realm of physics. Young devised an experiment that was, in its setup, strikingly simple yet profound in its implications. A source of light was directed at a screen, with an intermediate barrier containing 2 narrow slits. If light were composed of particles, individual particles should pass through one slit or the other, producing 2 bright spots on the screen behind. But if light were a wave, it would diffract through both slits, creating an intricate pattern of interference, alternating bands of brightness and darkness. Young performed the experiment, meticulously shielding it from external light. He directed sunlight through a small aperture to act as a coherent source, and when he observed the screen, he saw an unmistakable interference pattern, compelling evidence that light behaved as a wave. For over a century, this view remained unchallenged. But as has so often been the case in physics, quantum mechanics arrived to disrupt our understanding. Quantum mechanics revealed that nature is not continuous, but quantized, chopped into discrete units. This extended to light itself. Albert Einstein, in a groundbreaking insight, proposed that light was made of discrete packets, now known as photons. But this posed a fundamental problem. If light was composed of particles, how could Young's interference patterns still emerge? This duality, in which light exhibits both particle-like and wave-like behavior, remains one of the great enigmas of physics. The key to understanding it lies in the language of quantum mechanics. Classically, objects have well-defined properties. A stone is here, it moves at this speed, and its future position can be determined with certainty. But in quantum mechanics, this certainty dissolves. Instead of a definite position and velocity, an electron is described by a wave function, an abstract mathematical entity that encodes all possible outcomes of measurement, but does not specify a single, definite reality. The wave function is spread across space, encompassing all possible states. In 1926, Owen Schrödinger derived an equation that describes how wave functions evolve over time. Using this equation, we can predict how light, or any quantum particle, interacts with Young slits. Because wave functions behave as waves, they interfere with each other, producing the very same interference pattern observed in Young's experiment. Problem solved? Not quite. If we repeat Young's experiment today with modern detectors capable of registering individual photons, an astonishing fact emerges. Each photon is detected as a discrete particle on the screen. The light travels as a wave, passing through both slits simultaneously. Yet when it interacts with the detector, it manifests as a particle, appearing at a single point. This is not just true for photons, it applies to all quantum particles. And herein lies the crux of the issue. How does a smeared-out wave function suddenly collapse into a discrete particle? It was 2 of the towering figures of quantum mechanics, Niels Bohr and Werner Heisenberg, who first proposed an answer. Their approach, known as the Copenhagen interpretation, introduced an extraordinary concept. The observer plays a crucial role in determining reality. In this view, the wave function represents a probability distribution as first proposed by Max Born in 1926. The probability amplitude tells us where a particle is most likely to be found. But for this wave function to translate into the detection of a single photon or electron, It must collapse into a single outcome. When a particle is fired at the screen, its wave function fans out, passing through both slits. The wave function interferes with itself on the way to the screen, but upon measurement, it collapses into a single, localized particle. We cannot predict precisely where each photon will appear, only the statistical likelihood of different outcomes. While the Copenhagen interpretation has been confirmed through countless experiments, it has an unsettling feature. Nowhere in the mathematics of quantum mechanics is there a mechanism for wave function collapse. It must be added as an ad hoc rule, an unsatisfactory patch on an otherwise elegant framework. This unresolved issue, known as the measurement problem, remains one of the great mysteries of physics. Some have proposed that the very act of detection collapses the wave function. John von Neumann went further, suggesting that consciousness itself plays a role, that an observer's awareness is essential to defining reality. This radical idea raises bizarre implications. If consciousness is required to collapse wave functions, does that mean no quantum measurements occurred before the first conscious beings emerged? Could the early universe have existed in a superposition of states until intelligent life arose to observe it? Despite its popularity in quantum mechanics courses, the Copenhagen interpretation remains deeply controversial. Many physicists are uneasy about its reliance on an arbitrary collapse mechanism. Cosmologist Sean Carroll has described the notion of wave function collapse as an embarrassment to physics. Thus, alternative interpretations have been proposed, some of which lead directly to our Level 3 multiverse. The most controversial of these alternatives is the many worlds interpretation. In 1942, a 12-year-old Hugh Everett III wrote to Albert Einstein, asking whether the universe was governed by chance or by some deeper unifying principle. 12 years later, during a late-night discussion over the bizarre implications of quantum mechanics, Everett formulated what would become his most profound contribution to theoretical physics. His goal was simple: follow the mathematics of quantum mechanics to its logical conclusion, no matter how strange the implications might be. And with that, he sought to confront the measurement problem head-on. Indeed, the Copenhagen interpretation relied on the so-called Heisenberg cut, an arbitrary distinction between the microscopic quantum world and the macroscopic classical world, designed to keep the more perplexing features of quantum mechanics at bay. Hugh Everett III rejected this distinction outright. He dismissed the notion of wave function collapse entirely and proposed a radical alternative. To understand his reasoning, let us consider an experiment in a controlled laboratory setting. Traditionally, the experimenter is seen as separate from their apparatus, influencing the experiment by altering variables such as temperature or magnetic field while remaining an external observer. However, Everett realized that this distinction is fundamentally flawed. Everything in the laboratory, including the experiment itself, is composed of electrons and atomic nuclei, each described by its own wave function. Consequently, the experiment is not a single definite entity, but rather a superposition of all possible wave functions. And crucially, so is the experimenter. A complete quantum mechanical description of the laboratory must include the superposition of both experiment and observer. The entire system, the laboratory, the apparatus, the experimenter, is a superposition of all possible states. But if the observer and the experiment are entangled in this superposition, where does wave function collapse occur? Everett's realization was profound. The problem only deepens when we consider the entire universe. The universe itself is not an isolated system. It is the totality of existence. The universal wave function, therefore, must encode all the particles and interactions within it, including those that make up you. In Everett's formulation, the Schrödinger equation dictates how this universal wave function evolves over time, encompassing all possible futures. But if the universe follows a deterministic evolution via the Schrödinger equation, where does the randomness of quantum mechanics originate? Everett's answer was groundbreaking. The universal wave function does not merely encode our observed reality, it encodes all possible realities simultaneously. In this formulation, Every quantum event is not singular, but rather the branching point of parallel realities. The act of measuring an electron in a superposition of two states does not cause the wave function to collapse. Instead, the coherence between nearby universes is broken, and these universes decohere from one another. In some universes, the electron is found in state A. In others, it is found in state B. Since you, the observer, are also part of the universal wave function, there exist versions of you that observe state A and others that observe state B. In that moment, the universe is split, forming two distinct branches. And this happens at every quantum measurement, at every quantum interaction. Every probabilistic outcome is realized in some branch of the universal wave function. Individual universes with divergent histories crystallize out of the ultimate superposition. In the many worlds interpretation, these other universes are just as real as our own. In some, an alternate version of you exists, differing in subtle or drastic ways. In others, you never existed at all. The result is an infinite web of realities, each branching at every quantum event. At first glance, this may seem analogous to the level 1 multiverse, where vast parallel worlds unfold. However, the level 3 multiverse proposed by Everett is far deeper. Here, every branching universe can contain its own level 1 multiverse or even level 2 structures, nested infinities beyond comprehension. From the simple observations of Young's double-slit experiment, we arrive at a breathtaking conclusion. The many worlds interpretation gives rise to an endless sea of parallel universes. Naturally, such a radical idea has faced resistance. Some physicists dismiss many worlds as excessive, arguing that it postulates an unfathomable number of universes simply because physicists could not determine which version of reality was real. Nobel laureate Gerard T. Hooft famously remarked, "It would be a stupendous number of parallel worlds, which are only there because physicists couldn't decide which of them is real." Everett's insights were largely ignored during his lifetime. His thesis was met with indifference or outright dismissal, even by Niels Bohr himself. Disillusioned, Everett left academia after completing his PhD, working instead as a computer scientist. He died in 1981, never witnessing the resurgence of interest in his ideas. However, a new generation of physicists has embraced many worlds, recognizing it as one of the most consistent and elegant interpretations of quantum mechanics. To many, it is the only interpretation that follows quantum mechanics to its logical conclusion without invoking ad hoc collapse mechanisms. Yet, profound questions remain, chief among them, consciousness. What happens to the conscious self as universes diverge? Do distinct copies of an individual emerge in each branch, each retaining all prior memories? If so, what defines the continuity of identity across multiple realities? This is the domain where physicists and philosophers collide. Consider a thought experiment. A coin is flipped, and if it lands on tails, you are executed. If it lands on heads, you survive. Each time you flip the coin, you know that the probability of survival is 50%. If the Copenhagen interpretation holds, eventually you will lose this game. But in the many worlds framework, at the moment of each toss, the universe branches. In one reality, the coin lands on heads and you survive. In another, it lands on tails and you perish. With each subsequent flip, the multiverse continues to split. Yet, in at least one universe, there will always be a version of you that experiences a continuous sequence of lucky outcomes, an immortal observer navigating an improbable but real sequence of events. Does this mean that in the many worlds interpretation, you will always find yourself on the lucky path? Is consciousness bound to the thread of survival? These questions lie at the edge of scientific inquiry, blurring the lines between physics and metaphysics. It seems that we have reached the furthest limits of our exploration of multiversal theories. What could be beyond an infinite superposition of all possible universes? To answer that question, we must relinquish even our deepest assumptions about reality itself. For in the level 4 multiverse, we will confront the idea that the cosmos is not merely a physical entity. It may be nothing more than a mathematical structure, a dream woven from pure abstraction. Level 4. What is reality? At first glance, the answer seems self-evident. We are surrounded by tangible matter, solids, liquids, and gases. Yet, as we have seen time and again, our intuitive perception of reality is deceptive. If we probe deeper, all matter is composed of atoms, which in turn consist of subatomic particles such as electrons and quarks. But even these so-called fundamental particles do not provide the ultimate foundation of reality, for their interactions are governed by mathematical laws, expressed through equations that define the fundamental forces and the structure of the cosmos itself. This leads to an unsettling question: where do these mathematical laws exist? If reality is dictated by numbers and equations, then where is the framework that encodes these rules? It is here that we arrive at Max Tegmark's level 4 multiverse, a radical yet logically consistent proposition. This multiverse is not composed of space, time, or matter, but of pure mathematics. Every conceivable mathematical structure exists as a universe in its own right, forming an infinite ensemble of realities. Within this framework, all possible multiverses, from the quantum branches of many worlds to the inflating bubbles of level 2, are simply different manifestations of mathematical objects. The implications of this idea are profound. In many ways, the level 4 multiverse resembles the controversial simulation hypothesis, the notion that our reality is nothing more than an advanced computation executed on a cosmic supercomputer controlled by entities beyond our comprehension. However, in Tegmark's vision, there is no need for a physical machine. The mathematical structures themselves are the fundamental substrate of existence. Reality, in its purest form, is simply a self-contained mathematical construct. At this point, we are navigating the farthest edges of speculation, where theoretical physics blends into the philosophical. We began our journey by peering beyond the cosmic horizon, asking whether other universes might lie beyond our own. Now, we find ourselves questioning the very nature of existence itself. One thing is clear: the multiverse is not a single, well-defined concept, but rather an intricate web of ideas. Some are deeply rooted in established physics, while others drift perilously close to the realm of science fiction. Before we conclude our exploration, a word of caution is warranted. In public discourse, discussions of the multiverse often provoke fierce debate. Some physicists view it as an inevitable consequence of our best theories, arguing that eternal inflation, for instance, leads inescapably to a vast ensemble of universes. Others champion N-theory and the string theory landscape as the natural explanation for our universe's finely tuned parameters. Even relatively straightforward considerations, such as the nature of dark energy and the structure of the cosmic horizon, seem to point toward a multiversal framework. Yet, there are staunch opponents who reject the multiverse outright. To them, discussing unobservable universes is fundamentally unscientific. They argue that science requires empirical verification, falsifiable predictions that can be tested through observation or experiment. If parallel universes are forever beyond the reach of our instruments, they should be relegated to the realm of metaphysics rather than physics. However, neither side holds absolute authority. The truth is that multiverse theories remain in their infancy. While some theoretical foundations have been established, they are far from complete. Many key questions remain unresolved. How precisely did universes crystallize out of eternal inflation? Can string theory, despite its mathematical elegance, ever be experimentally verified? Does the many-world interpretation of quantum mechanics truly reflect physical reality, or is it merely a convenient abstraction? And can the level 4 multiverse ever be anything more than an intriguing mathematical conjecture? Despite these uncertainties, the possibility of testing multiversal ideas should not be dismissed outright. Advances in observational cosmology may one day uncover indirect signatures of parallel universes. Some researchers propose that scars in the cosmic microwave background might reveal evidence of past cosmic collisions, remnants of interactions between our universe and others in the higher dimensional bulk of N-theory. The geometry of the universe itself, if found to be perfectly flat and infinite, might lend further weight to the idea of an endless cosmic expanse. For now, however, direct evidence of other universes remains elusive. The search for parallel worlds is still in its infancy, and we cannot predict how our theories will evolve in the coming decades. It is entirely possible that the multiverse will forever remain hidden within the fog of the unknown, an idea tantalizingly out of reach, yet eternally fascinating in its implications. And so, we stand at the boundary of knowledge, gazing into the abyss of possibilities. Whether the multiverse will ever be revealed, or whether it will remain an enigma woven into the fabric of theoretical physics, is a question only time and relentless scientific inquiry can answer.
What drives humanity to measure the world in extremes? Why are we so captivated by the fastest, the largest, the most powerful? This obsession with superlatives reflects our unending curiosity about the limits of nature, and it is through such pursuits that we have shaped and reshaped the course of history. Yet, in our quest for the ultimate, we have also created some of the most destructive forces imaginable. One such example is the Tsar Bomba, a testament to both human ingenuity and hubris. But even this colossal explosion pales in comparison to the forces at work in the wider cosmos. Let us embark on a journey from the depths of human ambition to the incomprehensible scale of stellar cataclysms, all bound by the enigmatic force of gravity. On October 30, 1961, a Tupolev Tu-95V bomber flew over Novaya Zemlya, an archipelago in the Arctic Ocean. Its mission was unprecedented, to unleash the most powerful man-made explosion in history. Suspended beneath parachutes to delay its descent, a 27-ton bomb nicknamed the Tsar Bomba fell gracefully toward the Earth. The delay was essential, giving the bomber time to escape the ensuing cataclysm. When the bomb detonated, it released a staggering energy equivalent to 50 megatons of TNT, 3,800 times more powerful than the bomb dropped on Hiroshima. The mushroom cloud soared 60 kilometers into the sky, and the flash was visible over 1,000 kilometers away. Heat from the blast caused third-degree burns to those within a 100-kilometer radius. This unparalleled display of power was both a political statement and a sobering reminder of humanity's destructive capabilities. However, in the same year, the cosmos unveiled a spectacle that dwarfed even the mightiest human invention. Astronomers observed the death of a star in a galaxy 45 million light-years away. This was a supernova, an event triggered and a massive star exhausts its nuclear fuel and collapses under its own gravity. With its core unable to resist the inward pull, the star implodes at a fraction of the speed of light, causing temperatures to soar and resulting in an explosion that scatters stellar material across light-years of space. The energy released by this single event is beyond comprehension, outshining entire galaxies. Yet, even the grandeur of a supernova is overshadowed by an even rarer phenomenon, the hypernova. These extraordinary explosions occur when stars more than 30 times the mass of our Sun meet their end. The star's core collapses to form a black hole, and the remaining stellar material ignites under the influence of extreme gravitational forces and searing winds of nickel-rich radiation. Hypernovae are up to 100 times more powerful than supernovae, representing the pinnacle of cosmic violence. They are the most energetic events in the observable universe, fueled by gravity's relentless pull. Despite the seemingly boundless power of these stellar events, gravity's influence is surprisingly weak when measured against the universe's other fundamental forces. There are four such forces: the strong nuclear force, the electromagnetic force, the weak nuclear force, and gravity. The strong nuclear force binds protons and neutrons within atomic nuclei, making it the strongest of the four. The electromagnetic force governs interactions between charged particles and enables the radiation that lights and warms our universe. Even the weak nuclear force, which facilitates radioactive decay and stellar fusion, vastly outmatches gravity. In fact, gravity is weaker than the weak force by a factor of 10 to the 25th power, 10 trillion times. This apparent weakness poses a profound mystery, known as the hierarchy problem. How can gravity, so feeble at atomic scales, dominate the universe at large? To feel its effects, we require enormous accumulations of matter, such as planets, stars, and black holes. A simple ant, using the chemical energy in its legs, can defy the gravitational pull of an entire planet. Yet, when matter aggregates on a cosmic scale, gravity shapes the structure of galaxies, governs the orbits of celestial bodies, and even dictates the flow of time itself. The enigma of gravity's weakness has led physicists to propose extraordinary explanations. Some theories suggest that gravity's effects are diluted because it extends into dimensions beyond the familiar 3 of space and 1 of time. These additional dimensions, if they exist, could hold the key to understanding gravity's place among the fundamental forces. To unravel these mysteries, we must look to the earliest moments of the universe. In the seconds following the Big Bang, the fundamental forces were unified. As the universe expanded and cooled, they separated, a process that shaped the cosmos as we know it. The study of this period could provide insights into the origins of gravity and its apparent disparity with the other forces. Moreover, experiments at the frontiers of particle physics, such as those conducted at the Large Hadron Collider, aim to probe the nature of gravity and its relationship to the quantum realm. These investigations may uncover evidence of extra dimensions or reveal particles associated with gravity, known as gravitons. Such discoveries would revolutionize our understanding of the universe's fundamental structure. The quest to understand gravity is not merely an academic pursuit. It is a journey that touches on the very fabric of existence, from the smallest particles to the largest galaxies. Gravity shapes our daily lives, keeps our feet on the ground, and challenges our engineers as they reach for the stars. It binds the universe together, yet its true nature remains elusive. As we gaze upon the remnants of supernovae and hypernovae, and as we study the colossal black holes at the hearts of galaxies, we are reminded of gravity's dual nature, at once unimaginably powerful and deceptively weak. It is a force that defines the cosmos yet humbles us with its mysteries. To truly understand it, we must look beyond our own world, to the distant stars and the origins of time itself. Only then can we hope to grasp the full scope of this most fundamental of forces. Why do we fall? Gravity, the first of nature's forces to be recognized and quantified by science, is both the most familiar and the most enigmatic. For all its universality, gravity continues to defy complete understanding, eluding the grasp of even the most brilliant minds in history. To unravel its mysteries is to embark on a journey through the centuries, from the orchards of 17th century England to the curved geometries of spacetime, and onward to the frontiers of modern physics. The tale begins, as so many scientific odysseys do, with Isaac Newton. A solitary and meticulous man, Newton was as reserved in his personal life as he was prolific in his intellectual pursuits. The legend of his epiphany beneath an apple tree has become as much a part of scientific folklore as gravity itself. Whether or not an apple ever truly struck the ground before his contemplative eyes, the story captures the essence of Newton's genius, his ability to see the profound in the mundane. In 1666, during a plague-induced closure of Cambridge University, Newton retreated to his family home in Lincolnshire. There, in the quiet isolation of Woolsthorpe Manor, he laid the groundwork for his theory of universal gravitation. Why should that apple always descend perpendicularly to the ground, he wondered, as he later recounted. This simple question led him to imagine an invisible force extending beyond the Earth's surface, reaching across the heavens to bind the moon in its orbit and guide the planets on their celestial paths. Newton's formulation was elegantly simple. Every mass attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. This universal law of gravitation proved astonishingly effective. It explained the motions of the planets, the behavior of tides, and even the trajectories of comets. Yet, for all its predictive power, Newton's theory left unanswered the fundamental question: what is gravity? Newton himself was acutely aware of this limitation. That gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it, he wrote. While his equations worked, he could not fathom how one object could exert a force on another across empty space. Newton's reluctance to ascribe an intrinsic nature to gravity reflected his scientific humility and presaged the challenges that would confront physicists in the centuries to follow. For 200 years, Newton's theory reigned supreme. It guided explorers across uncharted oceans, enabled the construction of mechanical wonders, and illuminated the dance of celestial bodies. Yet, as observational techniques grew more sophisticated, cracks began to appear in its foundation. The orbit of Mercury, for instance, deviated ever so slightly from Newtonian predictions. This wobble, or precession, hinted at forces beyond the scope of classical mechanics. The turn of the 20th century brought with it a revolution in physics. Albert Einstein, a German-born physicist with an uncanny ability to see the universe in ways no one else could, turned his attention to the shortcomings of Newtonian gravity. Building on the insights of special relativity, Einstein proposed a radical new framework, general relativity. At its core was a simple yet profound idea: gravity is not a force in the traditional sense, but a manifestation of the curvature of spacetime. To grasp this concept, imagine a heavy object placed on a taut rubber sheet. The weight of the object distorts the sheet, creating a depression. Smaller objects placed on the sheet will naturally roll toward the center of the depression, not because they are being pulled, but because they are following the contours of the curved surface. Similarly, Einstein argued, massive objects like stars and planets warp the fabric of spacetime, and it is this curvature that guides the motion of objects within it. Einstein's theory was as mathematically intricate as it was conceptually revolutionary. It predicted phenomena that Newtonian gravity could not explain, such as the bending of light around massive objects and the precise precession of Mercury's orbit. These predictions were spectacularly confirmed during a solar eclipse in 1919, when astronomers observed starlight curving around the Sun exactly as Einstein had calculated. General relativity not only supplanted Newtonian mechanics but also opened the door to a universe far stranger than anyone had imagined. Yet, for all its triumphs, general relativity left its own set of mysteries in its wake. While it described the behavior of gravity on cosmic scales with unparalleled precision, it offered little insight into its origins. Why does gravity exist? Why is it so weak compared to the other fundamental forces? And how does it reconcile with the quantum realm, where the rules of physics take on an entirely different form? The weakness of gravity is one of the most perplexing puzzles in physics. Compared to the strong nuclear force, which binds protons and neutrons within atomic nuclei, gravity is astonishingly feeble. To put it in perspective, the electromagnetic force between two electrons is about 10 to the power of 36 times stronger than the gravitational attraction between them. This disparity, known as the hierarchy problem, suggests that we are missing a crucial piece of the puzzle. One possibility is that gravity operates on a fundamentally different plane than the other forces. Some physicists speculate that it may leak into extra dimensions beyond the familiar three of space and one of time. These hypothetical dimensions, though hidden from everyday experience, could dilute gravity's effects in our observable universe. Experiments at facilities like the Large Hadron Collider are probing these ideas, searching for evidence of gravitons, theoretical particles associated with gravity, or subtle deviations from the inverse square law at microscopic scales. Another avenue of exploration lies in the early universe. In the moments following the Big Bang, the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, are believed to have been unified. As the universe expanded and cooled, they separated, each taking on its distinct characteristics. Understanding this process could shed light on gravity's true nature and its role in the cosmos. Despite decades of effort, the quest to unify general relativity with quantum mechanics remains one of the greatest challenges in theoretical physics. The two frameworks are mathematically incompatible, yet both are essential for describing the universe. While general relativity governs the behavior of massive objects and the structure of spacetime, quantum mechanics dictates the interactions of particles on the smallest scales. Bridging this divide may require a paradigm shift as profound as Einstein's reconceptualization of gravity a century ago. One promising candidate for such a unifying theory is string theory, which posits that all particles are not point-like but rather tiny vibrating strings. These strings exist in a multidimensional spacetime, and their vibrations give rise to the fundamental forces and particles we observe. String theory suggests that gravity arises naturally within this framework, offering a tantalizing glimpse of how the quantum and cosmic realms might be reconciled. However, it remains a deeply mathematical and experimentally unverified construct, as elusive as the nature of gravity itself. In the meantime, gravity continues to humble and inspire us. It shapes the galaxies, governs the orbits of planets, and choreographs the intricate ballet of celestial bodies. It binds us to the earth, enabling the simplest pleasures of walking and running, and challenges us to reach for the stars. From the fall of an apple to the bending of starlight, gravity's story is one of discovery and wonder, a testament to humanity's enduring curiosity about the universe. As we stand on the precipice of new discoveries, the questions that Newton and Einstein grappled with remain as relevant as ever. Why do we fall? What is the nature of the force that binds the cosmos together? To seek these answers is to confront the very fabric of reality, to delve into the origins of existence, and to marvel at the profound simplicity and complexity of the universe. Gravity, the silent architect of the cosmos, awaits our understanding, a challenge that beckons us to explore, to question, and to dream. Ripples from the beginning of time. To detect ripples in the very fabric of space that have traveled across the cosmos for billions of years? Such questions evoke a profound sense of wonder, pushing the boundaries of our imagination as we attempt to understand the origins of our universe. These ripples, gravitational waves, carry whispers from the birth of the cosmos, offering us glimpses into epochs long before stars and galaxies existed. To follow their journey is to trace the history of existence itself, from cataclysmic collisions to the enigmatic beginnings of spacetime. A billion years ago, the Earth was a quiet, unchanging world. The planet languished in a geological and evolutionary stasis that scientists call the boring billion. Life, once brimming with innovation, had stalled. The planet's chemistry, climate, and geography appeared frozen, offering no clue of the monumental cosmic events occurring far beyond Earth's skies. In a distant region of the universe, two black holes, each over 30 times the mass of our Sun, were locked in an inexorable dance. Spinning ever faster, their violent embrace culminated in a collision so powerful it sent ripples through spacetime itself. These gravitational waves raced outward at the speed of light, carrying with them the energy of a cataclysm whose magnitude defies comprehension. But for over a billion years, these ripples passed unnoticed through the universe. Their arrival on Earth came not during the boring billion but in an age of human ingenuity. On September 14, 2015, a revolutionary instrument known as LIGO, Laser Interferometer Gravitational Wave Observatory, detected these waves. Just 2 days after being activated, LIGO recorded a fleeting signal, a chirp lasting less than a fifth of a second. This signal was the faint echo of the black hole collision, reaching Earth after a journey of cosmic proportions. LIGO's achievement was nothing short of extraordinary. For decades, skeptics doubted whether gravitational waves, predicted by Einstein's general theory of relativity in 1915, could ever be detected. Einstein himself was unsure if such waves, distortions in spacetime caused by massive gravitational disturbances, would be measurable. LIGO overcame these doubts by using lasers to detect minute changes in the lengths of its arms, changes smaller than the width of a proton. When a gravitational wave passed through the observatory, it subtly altered the distance between mirrors placed kilometers apart, producing the unmistakable chirp that heralded the arrival of waves from a billion-year-old event. This discovery was not just a technical triumph, it was a new way of observing the universe. For centuries, astronomers relied on light, visible, infrared, and other wavelengths to study the cosmos. But light can be obscured or absorbed, limiting our view of the universe's most extreme events. Gravitational waves, however, penetrate all matter unimpeded, carrying information from the darkest and most distant corners of existence. LIGO's detection opened a new window on the cosmos, allowing scientists to hear the universe for the first time. Subsequent discoveries confirmed the power of this new tool. In 2017, LIGO detected gravitational waves from a pair of merging neutron stars. This event produced not only gravitational waves but also gamma rays and visible light, enabling astronomers to observe it across multiple wavelengths. Such multi-messenger astronomy confirmed the violent origins of heavy elements like gold and platinum, forged in the aftermath of neutron star collisions. These discoveries validated Einstein's predictions and solidified LIGO's place in scientific history, earning its researchers the 2017 Nobel Prize in Physics. Yet, these detections only scratch the surface of what gravitational waves can reveal. They provide insights into the fundamental nature of gravity, a force that permeates the universe yet remains profoundly mysterious. Gravitational waves demonstrate that gravity is not an instantaneous pull between objects, as Newton envisioned, but rather a field that can ripple and carry energy through spacetime. This means that changes in a gravitational field propagate at the speed of light. If the Sun were to vanish, Earth would continue orbiting for 8 minutes, the time it takes for the information to reach us. Such revelations align gravity with the other fundamental forces of nature, electromagnetism and the strong and weak nuclear forces, which also operate as fields with wave-like properties. Light, for instance, is a ripple in the electromagnetic field. By studying gravitational waves, scientists hope to uncover connections between gravity and these other forces, potentially leading to a unified theory of physics. One tantalizing possibility is the detection of primordial gravitational waves, ripples generated during the universe's earliest moments. Current cosmological models suggest that the universe underwent a period of rapid inflation shortly after the Big Bang, expanding exponentially in less than a fraction of a second. This inflation would have generated gravitational waves, encoding information about the universe's infancy. These primordial waves would have traveled through spacetime for 13.8 billion years, reaching us as faint whispers from the dawn of time. Detecting such waves is a formidable challenge. LIGO and its successors, like the European Space Agency's planned Laser Interferometer Space Antenna, LISA, are being designed to filter out the noise of more recent cosmic events. LISA, with its kilometer-scale arms positioned in space, aims to detect waves from the universe's earliest epochs, providing unprecedented insights into the nature of inflation and the origin of gravitational fields. The detection of primordial waves could confirm key assumptions about the universe's birth. For instance, gravitational waves could reveal whether inflation was a gradual process or a sudden, violent event. They could also shed light on the nature of the gravitational field itself. Unlike the Higgs field, which gives particles mass, gravity is linked to energy and momentum. This distinction means that gravity could have existed even before the Higgs field emerged, influencing the universe long before matter acquired mass. Indeed, most cosmologists believe that gravity emerged during the Planck epoch, the earliest phase of the universe, when spacetime was compressed to scales smaller than a proton. At such scales, the classical laws of physics break down, and quantum effects dominate. Understanding gravity in this regime requires uniting general relativity with quantum mechanics, a goal that has eluded physicists for decades. New theories, such as string theory and loop quantum gravity, offer tantalizing possibilities. These frameworks suggest that spacetime itself may have a discrete, quantized structure, and that gravity arises from fundamental vibrations or connections at this microscopic level. While these ideas remain speculative, they highlight the profound connections between gravity, the fabric of spacetime, and the origins of the cosmos. Leaving our dimension. Lisa Randall's journey through Yosemite offers a striking metaphor for the forces that govern our universe. As she climbed the sheer rock face, she grappled with gravity, a force so weak that a single rope could suspend her against its pull, yet so unyielding that it accelerated her descent with unforgiving precision when her grip faltered. This duality of gravity's weakness and persistence mirrors its enigmatic nature in physics, the least understood of the fundamental forces, yet essential in shaping the cosmos. At the heart of our struggle to comprehend gravity lies a profound incompatibility between the two pillars of modern physics. General relativity, Einstein's masterpiece, describes gravity as the curvature of spacetime, a framework that elegantly explains the behavior of massive objects and the large-scale structure of the universe. Quantum mechanics, on the other hand, delves into the subatomic realm, where particles and forces obey probabilistic rules that defy classical intuition. Despite their individual successes, these theories clash irreconcilably when applied together, particularly at the Planck scale, a realm so minuscule that the distinctions between space, time, and energy blur. Most forces in nature, such as electromagnetism and the strong and weak nuclear forces, have been successfully integrated into the quantum framework. Each is mediated by messenger particles, photons for electromagnetism, gluons for the strong force, and W and Z bosons for the weak force. These particles arise from quantized fields that permeate the universe, their interactions governed by the elegant mathematics of quantum field theory. Gravity, however, remains the exception. Theoretical physicists have long posited the existence of a quantum particle called the graviton, a carrier of the gravitational force. Yet, detecting such a particle has proven elusive. The graviton's faint signal would require an impossibly large detector, one with a diameter surpassing that of our solar system, to measure its effects with precision. Complicating matters further, attempts to quantize gravity lead to mathematical divergences. When energy and momentum distort spacetime at quantum scales, the resulting feedback loop generates infinite energy densities that cannot be renormalized, a cornerstone technique used to tame infinities in other quantum fields. This failure suggests that our current frameworks are inadequate for describing gravity at the smallest scales. To address these challenges, physicists have proposed radical new theories. Loop quantum gravity reimagines spacetime not as a continuous fabric but as a network of discrete loops, each woven into a fine lattice at the Planck scale. This approach avoids the infinities that plague traditional models, treating gravity as an emergent property of spacetime geometry rather than a force in the classical sense. While promising, loop quantum gravity lacks the experimental evidence needed to confirm its validity. String theory offers another paradigm, envisioning the fundamental constituents of reality as tiny vibrating strings existing in a multidimensional space. In this framework, the three spatial dimensions and one temporal dimension we experience are merely emergent properties of a larger, more complex reality. String theory elegantly accommodates gravity, suggesting that its weakness arises from its connection to these hidden dimensions. Specifically, gravity's effects may be diluted as it propagates through additional spatial dimensions beyond our perception. Here, Lisa Randall's work enters the stage. Her groundbreaking theories extend the idea of multidimensional space, proposing that our universe is a three-dimensional brane embedded within a higher-dimensional bulk. In this model, the other fundamental forces are confined to our brain, while gravity resides primarily in a separate brane. The interactions we observe are merely the leakage of gravity from this gravibrane into our universe, explaining its apparent weakness. Randall and her collaborator Raman Sundram devised a mathematical framework to support this idea, showing that warped geometries in higher dimensional space could account for gravity's exponential decay across the bulk. This approach resolves the inconsistencies of supersymmetry, a theory that predicts partner particles for every known particle but struggles to align with observational data. By situating gravity in a separate brane, Randall and Sundrum preserved the elegance of supersymmetry while reconciling it with reality. The implications of Randall's theories are profound. If gravity truly originates in another dimension, it may never be fully detectable within our own. The elusive gravitons sought by particle physicists might simply have an infinitesimal probability of straying into our universe, making their detection a matter of extraordinary luck. Yet, the tantalizing possibility of higher dimensions reshapes our understanding of the cosmos, offering a glimpse into realities beyond our own. Despite its elegance, Randall's work, like all theories of quantum gravity, remains speculative. The mathematical consistency of her models is compelling, but experimental validation is essential. Just as gravitational waves were once dismissed as theoretical curiosities until LIGO's groundbreaking detection, so too might these multidimensional theories await their moment of empirical vindication. To this end, physicists around the world are developing instruments and experiments to probe these possibilities. Particle accelerators, such as the Large Hadron Collider, continue to search for evidence of supersymmetry in extra dimensions. Meanwhile, gravitational wave observatories and next-generation detectors like the Laser Interferometer Space Antenna aim to uncover new insights into the nature of spacetime itself. As Randall's theories remind us, the universe is far more intricate than it appears. From the immensity of galactic structures to the subatomic dance of particles, every level of reality is interwoven with mysteries that challenge our intellect and imagination. Gravity, the silent architect of the cosmos, may hold the key to unlocking these secrets. Whether its origin lies within our universe or beyond it, the quest to understand gravity is a journey that transcends dimensions, inviting us to explore the very foundations of existence.